Okay guys, last video for 9.8. To summarize page 5, because these functions can be defined in terms of n and x, you can use your same power rule, derivative, and integration rules on the function to find the integral and derivative of a power series. Now, one interesting thing about the integral and derivative of a power series is that it has the same center and the same radius of convergence, but it may or may not still include the endpoints. So you have to check the endpoints each time, but you don't need to check for the radius and for the interval again. So looking at number 5a, it says find the interval of convergence for the following functions. We'll start with the first one before we take the integral or the derivative. I believe we've done this one already. In fact, I think it's the first one from A from page 4. So it's A from the last video. But if you didn't see that, we take the limit as n goes to infinity using the ratio test. Be x to the n plus 1 over n plus 1 over x to the n over n. It simplifies to there's one extra x times n over n plus 1. So it's the limit of that thing. And so we find out that x needs to be less, since this is the absolute value, it's less than 1. So we go from -1 to 1. Now, we have to check the endpoints for all parts, but we're going to check it for this one first. So at -1, it'll be -1 to the n over n, which converges by the alternating series test. We showed this in the last video. And at 1, it was 1 over n, which diverged by p-series, or the p-series comparison. So what does that mean? It means this interval was -1 to 1, the interval of convergence, not the International Olympic Committee. But, so let's look at 5b. It tells you to find the integral of f of x, which was equal to that thing from part A. So what happens when we integrate x to the n over n with respect to x? That's when we integrate, we add 1 to the power and divide by the new power. So that becomes x to the n plus 1 over n, all divided by that new n plus 1, or x to the n plus 1 over n times n plus 1. Now, we could run this whole thing through all of the tests again. However, the rules state that it has the exact same radius of convergence. So we know that it's only from -1 to 1. The only thing I really have to do is test the endpoints. That's all I've got to do. So this is really x to the n plus 1. I'm going to write this as n squared plus n. Same bounds. So at -1, this would be the sum from n equals 0 to infinity of -1 to the n plus 1 over n squared plus n. Similarly, by the alternating series test, this converges by the alternating series test. Because it's alternating in sign and the terms go to 0. What about at 1? At 1, this becomes 1 over n squared plus n. This is going to also converge either by direct comparison or limit comparison. It will converge by, I'll say, direct comparison test. It is smaller than 1 over n squared, and 1 over n squared converges, so this one converges. So instead of 1 being excluded, 1 is now included on both ends. The last one is to take the derivative of the original. So what is the derivative of x to the n over n? Well, you bring the n down, the power goes down 1. What happens to the n's? They cancel. So this is the sum from n equals 1 to infinity of x to the n minus 1. Well, what does this look like? Well, we know it's still from -1 to 1, so let's look at the bounds. At -1, it'll simply be the sum from n equals 1 to infinity of -1 to the n minus 1 power. Now those terms are going to oscillate from -1 to 1 back and forth each time, which means they'll never hit an actual sum, so this diverges. And you can call it by the nth term, because the nth term is never 0. Now at 1, it becomes 1 to the n minus 1, which also diverges. So both of these endpoints aren't included for the interval of convergence, so it's just -1 to 1, neither one included. One thing to note, the integral is the most likely to include the bounds, and the derivative is the least likely to include the bounds. And if the derivative contains the bounds, all of the ones above it also include the bounds. If the integral doesn't contain a bound, then all of the ones below it won't contain that bound either. Like, notice here, this bound wasn't contained, so this one wasn't. Here, it was contained, so the one above it was also contained. So it's just an interesting little play. And that is all for this video.